Thank you. And I'm also going to get out of that corner. I know I don't like to be cornered like that. Okay, let me start my presentation for today. And do you have the contact information and my name in case you have questions afterwards? Okay, let me start with this question. What does the car shown in the picture have in common with a smartphone and a laptop computer? They all use rechargeable batteries, right? Today, we cannot live without rechargeable batteries in a world largely dependent of portable electronics and rechargeable batteries. What's more, with lithium-ion batteries, they have recently propelled the development of electric vehicles and its commercialization. And as you know, there are intensive research collaborations between universities and private companies trying to develop solid-state batteries and new energy materials. Materials that give us batteries that give us more efficiency and more power capacity. Now, there are different types of batteries, and there are pouch batteries, prismatic batteries, cylindrical batteries, and there are several research initiatives and publications in which you can investigate. There are pros and cons in each one of those. But the interesting thing is, okay, we have to, additional to develop them, find a way to inspect them. And that is the topic of my presentation for today. Specifically using 3D X-ray computer tomography, because it's a non-destructive technology that can see inside without cutting or slicing the battery. But that's not the only technology that you can use to inspect batteries in a non-destructive way. There are other techniques out there, like ultrasonic testing. There is also white light interferometry or white light devices, but there are limitations. For white light interferometry, they have a high resolution capability, but they are limited to the surface. And ultrasonic testing, they can certainly penetrate the part, but they are also limited in terms of resolution. X-ray computer tomography is the only technology so far that can scan across a long range of scales, from centimeters to nanometer range. And yes, there are other technologies out there, like electron microscopy and neutron microscopy, but still when you see a graph like that from one of recent publications, given the transmission of the X-ray and the penetration length into the material, still X-ray is one of the technologies, the only technology that can cover a large range, from centimeters to nanometers. And from the different X-ray CT technologies, there are several possibilities. There is X-ray macro CT, micro CT, nano CT, or combinations of them. And most of the technologies that we see out there are mainly micro CT and macro CT, but there are also some nano CT capabilities that can give you details to the nano scale. To give you a little bit of explanation of how those technologies work, here is a plot. This is the typical X-ray CT computer tomography system. It's composed of a flat panel, an X-ray source, and a rotational stage where you are going to place the part to collect different radiographs and reconstruct the part. But there are limitations in the fact that they basically use geometrical magnification. And that means that the resolution of those systems are dependent of the size of the sample. And generally, they are typically limited in the order of 20 microns, 10 microns. And if you make very small samples, maybe you go down to 2 microns or so. But it's very difficult to go down to a submicron level, unless you use a different type of system that we call X-ray microscopes. And the difference between the X-ray microscopes and the traditional X-ray CT is that these systems, additional to the geometrical magnification, have an optical magnification added to it with a series of optical lenses. So you have a combination of two magnification that increase the resolution capabilities. And that's how we can go down to nanometers resolutions. And let me just go back. I don't want you to miss this video. Oh, it's not playing. Let me see. Yeah, there it is. That is how you can scan a device like a smartphone and check inside of the battery without destroying the device. And check inside of the battery for the composition of the electrodes and see if there are any kind of defects, cracks or delamination that can be caused by charging and discharging cycles of several times in the battery. And there are other types of batteries, cylindrical batteries, and this is one example in which you can see with an X-ray microscope the type of imaging that you can obtain with that types of microscopes. You can see a clear separation between the different electrodes, the anode and the cathode, and the separation layers. And yes, you can make nice, cool videos in 3D and do some coloration for illustration, but the main thing is that you can assess anything inside with those 2D slices. And yes, you can label the anode, the separator, the collider, but the important thing is what you are looking into those images. And generally, you're looking for inclusions, particle inclusions, or any kind of defects like a crack. And I think if I go into the next slide, I might have a nice video that shows you a little bit of the workflow with those X-ray microscopes. When you use different zoom lenses to collect images without destroying the battery, you're still collecting a small portion of the battery, but you haven't physically cut the battery. It's just that you zoom in a region of interest to collect those images. And you keep doing that to gain resolution with different magnifications. And you can see in this one in particular, there are several inclusion particles that shouldn't be there. And I think in the next, you will see that we detected a crack inside of the battery. So those are the kind of things that you could do with an X-ray microscope that has these different zoom lenses and something that we call resolution at a distance, because you don't have to destroy the part or collect the smallest sample that you could to get the highest resolution. You can still get the resolution at that with the battery being intact, just because you take those zoom lenses and you zoom in and then you increase the magnification, so you increase the resolution. This is the typical workflow that you will see in an X-ray microscope. And it's not just about resolution, it's about contrast. The fact that we have the ability to tune the different imaging capabilities of those detectors to differentiate different densities of materials. You know that within a battery we have high density materials or low density materials that sometimes are very hard to detect with X-rays. But that's not the case here. Because we have those zoom lenses that have been designed particularly to have those capabilities at different X-ray intensities. And this is another example. This is for a pouch battery, and it's this similar workflow. You collect a full field of view, and you can see the part inside of the machine, a full field of view, and you get an idea, and then you start collecting zoom in with the 4x, 0.4x, 4x, and 20x. You see the image at 20x, and it's really amazing. You can even see the microstructure of the different particles inside of the battery. So that's one of the nice abilities of the X-ray microscopes in terms of getting this type of assessment without destroying the device. And you can create all kind of videos because you have the volumetric information and see the separation between those granular structures and see the packing. You know that if the packing is not very good, then you have low density energy packing, and that's not very good. And you also can check for other kinds of defects or delamination at the end of the battery. And using those different zoom lenses, then you can collect those images and overpose one over the other to get this type of images and make a comparison between a low resolution imaging and a high resolution imaging. Again, this is one of the most beautiful images is the quality of the image that you can collect with X-ray without destroying the part. And for batteries, aging studies are very important as well. So we did studies, for example, with a fresh battery and then a cycle battery 200 times. And you can see that the silicon has almost disappeared from the structure. And we were wondering also what happened in some of the regions after 100 cycles. And you can see that there was a cracked particle there that kind of pushed away the other particles around it. That was really an interesting detail. But it's additional to these observations, you can also see morphological changes on the batteries after you cycle them several times. And this is also very important to see if those electrodes are bending on the top or are going to touch each other. And this is something that we did with 1 cycle and 80 cycle cells. Calendaring is another process that is very important in batteries, and this is just when you are packing those cathode materials. Depending if you apply high pressure or low pressure, then you might have a good packing or too much spacing between the different particles that is going to deteriorate the energy capacity of storage of the battery. So that also is something that we can certainly do with the X-ray technologies. And if we go all the way to the highest resolution that we can develop, which is down to 50 nanometers spatial resolution, with one of the best systems we have designed, you can see this level of imaging in which you even see small, very fine details in the particles. You can see that they kind of crack. They are cracked, split in 2 or more pieces. And all of these, I've been focusing mainly in X-rays, but of course they make part of a very large portfolio of industrial instruments that we have in industrial microscopy, all the way from light microscopes to the X-ray microscopes that I have been mentioning, to electron microscopes down to 0.5 nanometers resolution. Electron microscopes, this is the best resolution that you can find in the market. But of course, the disadvantage is that you will have to slice the battery. And yes, you can create a 3D volume if you slice and take an image, slice and take an image, but X-rays has the advantage of being a non-destructive technique. And since as I started this presentation, the main advantage of X-ray as compared to many other technologies is the capability of scanning stuff from the centimeter range to nanometer range, to inspect all kinds of things that you can imagine in the battery, from the battery material all the way to the pack assembly, from the anode, cathode, separator, raw material, electron production, cell assembly, module assembly, pack assembly. And all of those details that you see there are in principle doable. You might need different types of systems, but those assessments are able with the X-ray technologies. And X-ray is not the only type of solutions. Of course, I cannot just forget to mention that there are other types as electron microscopes, light microscopes, CMMs, coordinate measuring machines, or even light scanners. All of them use different functions, but today I wanted to emphasize the role of X-ray technologies in the inspection of batteries. So if you have any questions, I'll be happy to answer.
Oh, Thank you so much for the talk. I think this is a really timely session, given there was a recall issue of GM and LG. So I have two quick questions, goes to all of you. So Elon Musk strongly recommended against the use of large pouch cells due to dangerously high probability of thermal runaway. That's about the news a few days ago. So do you agree with the statement? And my question number 2 is that any thoughts on GM-LG battery recall issue? So according to the recall document that I saw, there was an issue related to the anode tap area. So was it a preventable issue given if they use your technologies? Thank you.
All right. So yes, as I kind of stated in part of my presentation, right now I see a little bit of a battle in the different philosophies. There are the manufacturers that want to use flat batteries, and they say, well, they can store in a large flat battery that can be 300 millimeters long or 600 millimeters long, and have a more efficient way of storage energy. And that's a way of doing it. There is another philosophy that says, no, it will be better for me to pack a bunch of cylindrical batteries, because if I have a way to assess when one of those batteries fail, then I just turn that off and the car still will be functioning. So where are we going in the future? In reality, I don't know. It is a race, and we will see. But it's very interesting that there are different philosophies there, and each one of those has pros and cons. But what we have to do as inspection developer manufacturers is try to keep up with those developments and develop also technologies that can inspect those type of batteries.
I think just to add to that, I think the industry really needs a standardized cell format. It is ridiculous to keep going with so many different formats and so many different types of cells, and it just, I think the cell chemistries and all of that, that development is happening, and that's fantastic. But ultimately, when they go into a module, I think we need a standardized standardized cell format. That being said, with the ultrasound inspection method, we can detect on any type of chemistry or form factor.
So let me just build on that as well. So you're actually at a two-part question, and the second part was, what can we do to help? Would our equipment help that? And I think certainly having instrumentation that can have incredible resolution to see inside the cells, to diagnose and do get a better insight into what's going on is really critical. I think the point is that our job is to be an enabler to find the answers to those things. I don't think we're going to say that this machine could have found it and that machine couldn't have found it, but to make sure we have a full arsenal of ways to look at it on all different scales and be able to have software that can process the data or software that can collect and trace the data to help manufacturers figure out, I found the smoking gun, or I found the signal that alerts me to a problem that's going to happen in the future.
Yeah, and at the end of line, we need to inspect every cell for defects. So we need methods that are fast and that can be used at the end of line for inspection.
Hi, my name is Thomas Chung. I have a multiple-part question. So the first part is about, you did the ultrasonic inspection for wetting on the pouch cells. Do you think that's applicable to cylindrical cells as well?
Yes, we have data on cylindrical cells as well.
Okay. And then the other part is, CT scanning is pretty time-intensive. Do you see that process being 100% inspection of cells, or like a partial quantity of it? And can it also get through steel or stainless steel cans, especially for cylindrical cells, because that's much more highly dense?
Yeah, thank you. And you are right to the point, so the weaknesses of the method. And we are working certainly of improving those. There are physical limitations that you're not gonna ever overcome in terms of penetration depth. For example, X-rays, the way they work is they start decaying once they start penetrating a material, and there are two factors that drive that decay in intensity. One is the length of the material, and then the material itself, the atomic number of the material. So if you imagine that you can put X-rays as a plastic, it's easy to go through. But when you start putting casing materials that are more heavy in terms of metals, then it's more difficult, and then there are limitations of size. There are two ways to address this in terms of penetration depth, is going higher in energy. So if we talk about putting instead of 225 or 450 kV, and some people even go higher. But then there is limitation in the resolution. So there is a game there, but it's possible. Now the other question that you are, or the other item you mentioned is the speed. And there are solutions out there that can do CT scan under a minute, but they also suffer of resolution. And once you start increasing the resolution, then you increase the scan time. So there is a game there, and you have to deal with them. We keep improving in our sites. For example, we're leveraging now in machine learning or deep learning technologies. And the way we traditionally reconstruct, and most manufacturers do the reconstruction, is using an algorithm that is called Feldkamp or FDK, that was created in the 1980s by some group of 3 people that used to work at Ford for cone beam CT. And it's the most efficient algorithm, but it needs a lot of projections. So you need to collect over 1,000 projections or more to reconstruct a good CT scan. If you use deep learning, you could get away with maybe 300 projections and speed up the scanning by 4 times, 8 times, and we have seen even 10 times. And we have seen that in batteries. So that's a new development. In fact, we launched a package, and we're planning to come with more.
Hi, Mike Wise, like Daimler Truck. I've got a question about the ultrasound. You mentioned right now that you're doing measurement on the cell assemblies, especially during the electrolyte fill process, but in the future that you're planning to look at defect detection in the electrode manufacturing process.
That's right.
With the limitations on resolution in ultrasound, can you hint a little bit what you would actually be measuring? Would it be similar to like an eddy current crack detection, or how do you plan to approach that problem?
Yeah, so that's a really good question. The resolution limitation can be overcome by going to higher frequency ultrasound technologies. And then the thing that we will be inspecting is subsurface impurities, agglomerates, delamination, which optical methods cannot pick up. So that's our key focus for production with electrode inspection.
Thank you for your time and all the information here. Without being familiar with the actual machines that are doing these and knowing the needs on the floor sometimes, are these pieces of equipment mobile, or is there any flexibility that are we going in the direction of having like something handheld that can be mobile in a facility if something happens, taking it from one part in the building to another? Or are these completely stationary where you have to hook up the one cell to each machine? Does that question make sense?
Who is the question directed to?
Yeah, I understand.
Like which one of these, are any of these technologies mobile?
Basically, she's asking if any of the systems that we develop are stationary or they can move to the manufacturer in different rooms. So I can start answering that. Given the regulations that exist with X-ray, most of the X-ray systems are stationary. The most mobile that you can do them is to put it in the manufacture floor, for example, is that you can make rotational stages. So you can rotate the detector, and you can put a robot arm that kind of turn the X-ray source and the detector and then the part. And that's mostly what you can do. So you can load and batteries and put them back and say they are okay or not. But in terms of mobilizing, yes, you can move the system from one room to the other, but there is a full process. It's not just like you go with it the next morning when you come to work.
The ultrasound systems that we've developed are all benchtop tools, which are on a cart, and the ones that we have deployed with our customers are pretty mobile. So the footprint is maybe about 2 feet by 2 feet, and they're mobile on a cart. We plan, as we scale from the process development stage to go to pilot scale, we would need automation, to do the cell handling, and that will be an additional add-on, but the footprint of the system should not change all that much.
Thank you.
Any other questions? Going once, going twice. All right.
Thank you.